right? I thought there'd be data. Is anyone out there?
Hello, welcome back to Mathematical Statistics. So last time we kind of built a test intuitively and we defined a bunch of things. Okay, so last time we defined alpha, the level of significance or size, to be the probability of what is known as a type 1 error. And this is the probability we're off to a great start today. I can't even write a P for probability. This is the probability you reject the null hypothesis when you shouldn't because it's true. And we only defined this for a simple null hypothesis. I spent quite a bit of time last time talking about simple versus composite and that it's not as simple as just saying an equal sign versus an inequality. But I'm going to sort of talk that way. I'm having really a lot of trouble forming words. I'm going to use the word simple kind of conversationally today and not so specific to the definition from last time. Anyway, suppose now we have a composite null hypothesis. We need to define this level of significance and find a test. So I'm going to do the same example we had. We've got x1 through xn, IID, normal, normal mu sigma squared. We've got that sigma squared is known. And I want to test something like the null hypothesis is that mu is less than or equal to 3 versus the alternate hypothesis that mu is greater than 3. So before, we were kind of stuck with the very simple null hypothesis that mu is equal to 3. Okay, so step 1 is to decide on a statistic. And at this point in the course, I'm usually giving you this, like I say, make a hypothesis test based on the minimum or based on the sample variance. In this case, we're going to use the sample mean because it's a test about the true mean. And step 2 is going to be to come up with a rejection region or the form of a rejection region. So this is where you look at the statistic that you're going to use and you look at what would happen to that statistic if the alternate hypothesis were true. So in this case, the alternate hypothesis is that the mean is larger than 3, so just large in some sense. And so that would reflect in the statistic by it coming out large. Right, so the form of the test is going to be to reject the null hypothesis in favor of the alternative. Writing that part of the phrase was important last time because we didn't cover the whole parameter space. We had mu equals 3 versus mu is greater than 3. Here it's not really important to write this part. If x bar is greater than c for some c to be determined. Okay, so step 3 is going to be to step 3 is going to be to find C, and step 4 is going to be to give the conclusion. So we find C using alpha, the level of significance of the test, or the size of the test. And so what I'm about to write here is going to be wrong. I'm going to have to correct it. But given what we know so far, alpha is the probability of a type 1 error. And this is the probability you reject the null hypothesis when you shouldn't because it's true. And for us, rejection is going to mean that x bar is greater than some c. And when it's true, means that mu is less than or equal to 3. And here's where we have a problem. In our last example, the null hypothesis was very simple, and it was just mu equals 3. And so I could take that information and figure out this probability by standardizing it, subtracting the mean and dividing by the standard deviation and turning it into a standard normal. But for this problem, I don't know what that mean is, so I can't begin to standardize this. And this is why the level of significance is defined differently for a composite hypothesis, which actually will jive with our original definition. So here is the definition, sort of sticking in the middle of this example. For any null hypothesis, kind of want to say composite, but this will work in the simple case, the level of significance or size of the test is still denoted by an alpha and is now defined a little bit differently. Defined as follows. So it's going to be the maximum probability of making a type 1 error. And the type 1 error is the null hypothesis is true and you rejected it. So we want to maximize this over all the parameters in the null hypothesis. So for this example, we would, let me do it kind of generally. We would have a theta instead of a mu, and we would take the max over all the theta in the null hypothesis set, which last time I called capital theta sub 0. And so this actually does not contradict anything we said last time, because, let me stick with another color since I'm not back to the example. So if we're testing the null hypothesis that mu equals 3, nice and simple, then, and maybe we're looking at x bar, and maybe we're deciding to reject when x bar is greater than c. Maybe we're doing the exact example from last time. Then alpha would be the maximum over all the mu's, like in the null hypothesis, of the probability of making a type 1 error. The thing is that there's only one mu in there. This is just the singleton set, mu equals 3. So we're plugging mu equals 3 into the probability. We're not maxing it out over a bunch of mu's. But it does work with this definition. Okay, so back to the example. This is not quite right because we couldn't figure out how to compute this probability unless we knew exactly which mu or which of the simple hypotheses contained within the null hypothesis was true. So I'm going to go back to step 3. So we want to find C using alpha. And so alpha is the maximum over all of, in this case, mu in the null hypothesis, in this case, less than or equal to 3, of the probability of that we reject the null hypothesis when, and I'll have shorthand for this in the next line, but when the parameter is mu, and then we're looking at all the mu's less than or equal to 3. So a shorthand way that we're going to use to write this down is the maximum over mu less than or equal to 3, the probability you reject the null hypothesis, and then a semicolon mu. So this probability is a function of mu that we're going to maximize over the null hypothesis set. Okay, so continuing with this specific example, this is the max over mu less than or equal to 3. Rejection for us meant that we're looking at x bar and it is greater than some c. And I'm saying when the parameter is mu, and we can work out this probability, forget about the max for a moment. If we have a normal distribution to start with, then x bar is still normal, not using the central limit theorem, but just a linear combination of normals is normal. And if the mean is mu, which is what this probability statement is saying, we know that the mean for x bar is also mu, and the variance for x bar is our known variance divided by n. So I could standardize this and turn this into a standard normal random variable, and I will. So this is the max over mu less than or equal to 3, the probability x bar minus mu over sigma over the square root of n, and on the other side I'm going to use the I'm going to do the same exact thing when the parameter is mu. And now the thing on the left is a standard normal, so we can call it Z. I know for those of you that have had hypothesis testing, this is insanely slow, but my next example, I want to take it to other distributions, which hopefully you haven't seen too much of. Okay, so now I can stop writing that semicolon mu, because knowing mu is what told me that this statistic has a normal 0-1 distribution. So I'm just going to write over here where Z is normal 0-1. Okay, we can't write this probability down in closed form. We do have an expression for it. And I don't know if you, this is actually an unnecessary step. So let me just make this kind of a parenthetical step. We could, if we wanted to, rewrite this as 1 minus the standard normal CDF evaluated at C minus mu over sigma over the square root of n. But I don't need to, and that's because that capital phi is the CDF, or a standard normal. Okay, so without writing that, going back to this line, let's talk about maximizing it over those mu's. If you just look at the mu in the problem, then as mu gets larger, this whole number gets smaller. And so we're talking about the probability of P being greater than a number that is getting smaller and smaller and smaller as mu gets larger. So the largest mu equals 3, will make this smallest, and that will maximize this probability. So by inspection, we see that this probability is maximized at mu equals 3. So again, I'm saying by inspection. Sometimes when we get to do the more general test that we're going to do, we have to use calculus here and actually maximize something. So the max probability happens at mu equals 3. Okay, so this whole thing was equal to alpha, and our goal is to find the C. And so this is exactly the problem we did last time. We want a number that we are above with probability alpha, and that means that the C minus 3 over sigma over the square root of n has to be equal to our critical value Z sub alpha, which is what we're using to denote a number on the standard normal curve that cuts off area alpha to the right. So we end up with the exact same C. We get 3 plus Z alpha sigma over the square root of n. And step 4 will be our conclusion, or our rule. We're going to reject the null hypothesis in favor of the alternative if x bar is greater than this value. Reject the null hypothesis in favor of the alternative when x bar is greater than c, but we just found c to be 3 plus Z sub alpha sigma over the square root of n. So basically the same test, but we define alpha differently for a composite null hypothesis. And for most problems in an ordinary statistics book or textbook, the probability of rejecting this guy is going to be maximized at the endpoint of the region. But I could make something up. I can make up a weird function. I can make up a problem so that I have a weird function of mu there that has some kind of, maximum before 3 in theory. Okay, so what is the probability of a type 2 error? So in the table, that's the case where the null hypothesis is false and we make the mistake of failing to reject it. Now, if the alternate hypothesis is composite, we run into the same problem that we did with the null hypothesis being composite using our original definition of alpha. So the beta probability should actually be defined more generally as the maximum probability of making a type 2 error. So suppose we continue this problem and we want to know beta. So beta is going to be defined to be the maximum probability of a type 2 error. And the type 2 error was the null hypothesis is false and you fail to reject it. So this maximum is going to be taken over every place where the null hypothesis is false in this example, mu greater than 3. So this is the same thing as saying the null hypothesis is false. And the type 2 error is you fail to reject the null hypothesis when it's false, and we're kind of maxing over all these different places where it can be false. So to continue for this particular example, this is the maximum over mu greater than 3. Now we already came up with a test, and it's right at the top of the screen right now. So we're going to have a type 2 error if we, let me write this out in words in one more line. We fail to reject the null hypothesis when the parameter is mu, and then the fact that this is maxed over all of those mu's is taken care of when the null hypothesis is false. Okay, so our rejection rule is right up here. So I'm going to fail to reject whenever x bar is less than or equal to that number. So I can continue down here and write this as the maximum over mu greater than 3. The probability x bar is less than or equal to 3 plus z alpha sigma over the square root of n when the parameter is mu. Okay, so in this probability without the maximum, I kind of have fixed or have given mu. So let's go after this probability. I still have that x bar is normal with mean mu, and this is the exact mu. Mu is mu, and variance sigma squared over n. So I'm going to standardize it, turn it into a z, and see what we get. This is the probability x bar minus mu over sigma over the square root of n is less than or equal to 3 plus z sub alpha sigma over the square root of n minus mu over sigma over the square root of n when the parameter is mu. And then the thing on the left is a standard normal, so I'm going to call it z. This is the max over all mu greater than 3 of the probability that z is less than or equal to 3 plus z alpha sigma over the square root of n minus mu over sigma over the square root of n. Right, so again, we want to maximize this, and we're just going to do it by inspection. The mu here, oh, that was highlighting. The mu here, we have a negative mu. So here I want to look at mu's getting larger and larger, like sort of starting at 3. And I really should have maybe started this differently. This maximum is not going to exist. Technically, it's a supremum, which is the least upper bound. I'll go back and do that next time. I don't want to change this problem. So as mu gets larger, this number gets smaller, and we have the probability that a standard normal is less than something that's smaller and smaller and smaller, right? So the standard normal is less than this, or is it less than this, or is it less than this? Those probabilities are going down. So we get the maximum probability when mu is largest. So, I'm sorry, when mu is smallest. Mu is smallest. So again, by inspection, this is the probability that z is less than or equal to 3 plus z sub alpha sigma over the square root of n minus 3 over sigma over the square root of n. And that simplifies quite a bit. And again, that was by inspection, but sometimes you might have to do calculus at this point. This is the probability z is less than or equal to, and everything cancels out there except a little z sub alpha. And the definition of little z sub alpha was a critical value on the standard normal curve that cuts off area alpha to the right, and therefore area 1 minus alpha to the left. So remember what this was. We did get beta to be 1 minus alpha. And I did say last time that that does not have to be true. And I still insist it does not have to be true. It just happened to be true here. And that happens whenever these maximums for alpha and beta occur at the endpoint, at the boundary between the null and alternate hypothesis. Any questions? Oh, yeah.
I had a quick question, not about that, but just should our definitions for alpha and beta be in terms of soups and not in masses?
Yeah, they should.
Okay.
Yeah, I forgot who I was talking to for a second. You're the mathier group. So it should be soups, but you're not going to see that anywhere, like even in other textbooks. I don't know why. But yeah, this thing does not actually have a maximum over this infinite half open interval. So if you don't know what we're talking about supremums, which are least upper bounds. So the largest this gets is when I plug in mu equals 3, but it doesn't quite achieve that because I'm not allowed to plug in mu equals 3. But that is the smallest upper bound I can get. Other questions?
I'm a little surprised that the beta turned out to be so large.
It's awful.
Yeah, it seems really bad.
Yeah. Yeah. So if you want to set both alpha and beta, in MathStat, we don't really want to spend time on this. This is something you do when you're actually performing hypothesis tests and doing data analysis. But we decided to pick an alpha, right? So we choose alpha, and then that gives us a cutoff, C, and it gives us the test. And then this automatically gives us a beta. And we're just kind of stuck with that. But if you want to choose both alpha and beta, which is what I think you'd really want to do, then you need to free up another parameter of the model. So usually it always is sample size. If you want to set both alpha and beta, then your rejection rule at the end is going to be, you need to take a sample of this size and reject if X bar is greater than this number. So RC is like kind of a free parameter that is determined from alpha. But if we free up the sample size, N, we can also, actually not always, you can't always solve this, but we can also usually set the beta that we want, as well as alpha. Yeah, that is a ridiculous probability of making a type 2 error. It's an error, right? And if your alpha is a 0.05, then you've got a 95% chance of making a type 2 error.
I guess assuming the null hypothesis is wrong.
Yeah, assuming the null hypothesis is wrong. That's right. Type 1, type 2, yeah, assuming it's wrong. Okay. So let's see if we can apply our skills to a problem that you don't see in a typical data analysis class. So here's a new example. And we're just going to work through this and try to figure out a test of size alpha based on one statistic or another statistic. And that is, I'm going to take IID exponentials with rate lambda. And suppose I want to test the null hypothesis that lambda is, let's just go with less than, just like before, less than or equal to some lambda naught, where lambda naught is fixed and known, and the alternate hypothesis that lambda is greater than lambda naught. So this lambda naught is known. With size or level of significance alpha. Okay, step 1 is to choose the statistic you're going to use. And given what we've already seen about the exponential distribution, we've been using two things. We've been using the minimum of the exponential a lot because it's easy to work with. It's another exponential. And we've been using X bar, the sample mean. So we have to choose one. And I am going to make this based on the minimum so we get a nice exact result. And then we'll talk about what happens with the sample mean, which will lead us to the conclusion of this lecture. How do you compare two different tests of size alpha? Okay, so let's say it was given based on the minimum that I only repeatedly use because it gives nice examples. It's easy to write down. So step one is to pick a statistic, which is done. Right. And step two is to set up the form of the so-called rejection region. This is also called the form of the test. So this is where, just like before, you want to look at your statistic and you want to say, how will this statistic come out in the data if I should be rejecting my null hypothesis? That is, if lambda is really much larger than thought, what will this statistic look like? And we talked about this last time. There's like an inverse relationship here between lambda and the things that come out of it. The mean for this distribution is 1 over lambda. Also, the PDF starts at lambda and goes down. And we drew a picture last time where we started at a higher value of lambda, and that means it shoots down faster because the total area is 1, and that puts more of the area down towards 0. So, completely by looking at this alternate hypothesis, I will conclude, given that I'm using the statistic, that I want to reject the null hypothesis in favor of the alternative if the minimum is small. And that's, again, because larger values of lambda will give you smaller values of the data. So if I had based this test on the maximum or the sample mean, the form of the test would still be the same, because the larger lambda is, the smaller all values coming out of that distribution are. The maximum is smaller than it would be with another lambda in the null hypothesis, the sample mean, everything like that. Okay, so more specifically, i.e., I'm going to reject the null hypothesis if the minimum is less than C or some C to be determined. And that's where step 3 comes in. Okay, so we want to find C, and we use alpha. And in this case, I do have a composite null hypothesis. So our alpha definitely needs that max in it, although you'll never go wrong by putting that max in it. So alpha is going to be the maximum over all of the parameters in the null hypothesis. So over all the lambdas less than or equal to the fixed lambda naught of the probability of a type 1 error. And a type 1 error means you rejected the null hypothesis when you shouldn't. So this is the maximum over all lambda less than or equal to lambda naught. The probability that X minimum is small, because that is the form of the rejection rule we came up with. So smaller than some C when the parameter is lambda. This is what's important from this course, like how to develop your own test, not how to do a hypothesis test involving the normal distribution. So if the parameter is lambda, this tells us that x1 through xn are IID exponential with like a fixed rate lambda, like it's known to us in this probability statement. And this gives us that the minimum is another exponential with rate n times lambda, something we've seen quite a few times. And so this probability is the CDF of an exponential, right? The CDF of the exponential with rate n lambda is 1 minus e to the minus n lambda x. So I'm just going to use that up here. This is the maximum. So there's no standardizing, something people always not you guys, but in like a lower level course, they're like, why didn't you subtract the mean? And the reason is we're just trying to compute the probability any way we know how. And for normal random variables, we turn it into a standard normal. But this one, I've got the CDF, or I could write it as an integral in general. So this is going to be 1 minus e to the minus n lambda times c. And then we look at this as a function of lambda. And as lambda gets larger, this e gets smaller, which makes 1 minus this e get larger. So again, we have an increasing function of the parameter. This is an increasing function of lambda by inspection. And again, if it's not obvious, you would actually have a function that you might end up plotting and taking derivatives of to maximize. So I get to plug in lambda naught, the largest value of lambda over the region in which I'm trying to maximize it. And this was set equal to alpha. So we want to solve for c, and we're done with step 3. So c is -1 over n lambda naught times the log of 1 minus alpha. And so step 4 is just to bring it all together and say what your test is. So I want to reject a null hypothesis in favor of the alternative, which is not important unless your two hypotheses do not make up the whole parameter space. If the minimum is less than -1 over n lambda naught times the log of 1 minus alpha. Does this even make sense with the negative? It sure does, because alpha being a probability, that 1 minus alpha is between 0 and 1, so that's negative as well. And we're done with our test. But is it a good test? Well, actually, are there any questions about this test? So is it a good test? I think we saw back when we were trying to estimate lambda that the estimator based on x bar was better than the estimator based on the minimum. And we will see here that the estimator based on that the hypothesis test based on x bar is better in some sense than the hypothesis test based on the minimum. So I think I'm going to leave, what time is it? Yeah, I think I'm going to leave this one as a homework problem because I don't have many at this point that are nice and workable. So we can make another test for this exponential case of size alpha based on the sample mean. And it would start off the same way because we want to reject the null hypothesis when the alternative seems true. And the alternate hypothesis is saying lambda is large. And large lambdas give you smaller values coming out of this distribution. And that includes smaller values coming out of the sample mean. So the form of the test is going to be to reject the null hypothesis if x bar is less than some C1 or D or whatever. And so you can use your definition of alpha to find C. And because this is going to involve the gamma distribution on your homework, I'm going to have you find C in terms of a chi-squared critical value. And then you will have a different value of this C or C1, but you'll also have a test of size alpha. And so the last thing I want to talk about today is how do we compare these tests? How do we say one is better than the other? Last time I defined the concept of the power of a hypothesis test, and I'm actually not interested in that at all, and I will never use that word again alone. I will say power function, which is related. So let's define the power function of a test. Okay, I'm going to use a gamma. There isn't really a common letter for this. Sometimes I see a K a lot of the times. I don't know where the K comes from. But it's going to be a function in general of the parameter. And this is just defined. This is the definition. Defined as the probability we reject the null hypothesis when the parameter is theta. And this doesn't mean that theta has to be from the null hypothesis or the alternate. This is a function of all theta in the parameter space. So let's find the power function for the exponential test that we just did based on the minimum. Okay, so in this case, I'm going to have my parameter is lambda, and rejecting the null hypothesis means that we looked at the minimum and it was small, and in particular, it was below -1/n lambda naught times the log of 1 minus alpha when the parameter is lambda. So if the parameter is lambda, then that tells me that the x's come from an exponential distribution with rate lambda, and that tells me that the minimum has an exponential distribution with rate n lambda. There's my rejection rule, right? Yeah. And so this is again the CDF for an exponential with rate n lambda. So I get 1 minus e to the minus n lambda, but I plug in all of that stuff. -1/n lambda naught log 1 minus alpha. Because that is how you compute the probability that the minimum is less than this number. Okay, so I'm going to just simplify this, negatives, negatives, ends, ends. If you rewrite that log as log 1 minus alpha raised to the lambda over lambda naught, what I wanted, and yeah, then we can take e of it, and our ends disappear, huh? 1 minus alpha to the lambda over lambda naught. I think I did that right. This is a strange power function because it doesn't depend on the sample size, which is kind of lines up with the saying the minimum is not going to be a great thing to base the test on. In general, there should be an n in there, but it is a function of lambda. And if you graphed it as a function of lambda, for the exponential, the lambda has to be greater than 0. I'm going to put down the fixed lambda naught that's given in the problem. And the power function is just the probability we reject the null hypothesis when the parameter is lambda. And this is the region where the null hypothesis is true, and this is the region where the null hypothesis is false. And this probability has to be between 0 and 1. So this is probably going to look like, I don't know what that looks like. So it's going to be something that has to be small here and large here. So probably something like this. I don't know, I have to actually graph that. There's a fixed alpha and a fixed lambda naught. And so this is me graphing this like function of lambda. This is not a CDF. It doesn't have to look like this. It doesn't have to be strictly increasing or strictly decreasing. But definitely if the hypotheses were the other way around, so lambda greater than or equal to some lambda naught versus lambda less than lambda naught, then this would be where the null hypothesis is true, and this would be where it's false. So we'd want something high here and low here. So this doesn't have to look like this. It could look very strange. It could actually, in theory, be some kind of U shape, which would be a horrible test. But again, this is the probability we reject the null hypothesis. And check this out. If you look at only the region where the null hypothesis is true, the maximum probability of rejecting the null hypothesis is right here. So that means that this height on this graph has to be alpha, the maximum probability of rejecting the null hypothesis when it's true. But let me just draw another power function just to say that if you have something that is lower here and higher here, then this line is a better test. And I strongly suspect you will see a better test when you look at X bar on the homework. And so we ultimately want to go for the uniformly most powerful test, and that's where the terminology most powerful comes from. We want it to have, this is the power function, we want the test to have high power whenever the null hypothesis is false. And we want it to have the highest power you can actually have when the null hypothesis is false. That color is not showing up. And be really low here. So we're going to go for the all-time best test. And it's entirely possible that you can make two tests that you can't compare directly, just like we talked about two estimators with variances that are not comparable. You can't say that one is smaller than the other for all theta. I'm going to end it there because I was really struggling to come up with words the entire time. I don't know what's up with me. We are done. Next time, we're going to start estimating.